Our speaker this evening is Professor Richard C.J. Somerville, who is Professor of Meteorology and Director of the Climate Research Division at Scripps Institution of Oceanography. He did his undergraduate work at Penn State, did his PhD at NYU. He's been on our faculty since 1979. He is a specialist in sort of fluid dynamics, particularly the fluid dynamics of fluids that are relevant to the Earth, the air, the water, and so forth, and doing very complex mathematical and computer modelings of the behavior of all of those fluids. He's highly distinguished. He's been recognized in many areas. He's fellow of the American Association of Advancement of Science. He's a fellow of the Meteorological Society, American Meteorological Society. He's written very widely, as you might imagine, on these extremely difficult topics. But he has also written a book, which I'd like to promote. I recommend my undergraduate students read this book. It's called The Forgiving Air, Understanding Environmental Change. Neil Morgan says it is a stunningly readable book, and I agree with that and strongly recommend it to you. Please join me in welcoming Richard Somerville. Richard?
Well, I want to thank all of you for coming. I'm flabbergasted and flattered. To set tonight's topic in context, I think it's helpful to remind ourselves of the paradigm shift that's been going on in Earth science. We think now of Earth system science and the topic of global change, and these are some of the precepts of that paradigm shift. One recognizes now that change is the norm. It's not the unusual thing. It's what we expect in Earth systems. As an example, ice ages come and go on geological timescales. But this time is different from our grandparents' time in that it's our era in which human beings, who have always been fascinated spectators at this great natural pageant of climate change, have now come up out of the audience onto the stage and begun to play a role. And in many of the areas that we'll be talking about tonight, and in others that we won't have time to, it's become clear that people are now not the only actor, but they are part of the mix that causes global change. The third bullet there says that Earth systems are linked, and we'll be seeing that throughout the talk tonight. We can't separate one part of system Earth from other parts, and therefore things often have remote and unexpected consequences. Global change impacts all of life on Earth, whether you're a tree, or a sponge, or a human being. Global change will have an effect on you and the ecosystem of which you're a part. And a corollary of that is that local changes, things we do locally, have global consequences. And that, again, is also new in our era. There's always been, for example, pollution problems on Earth. People were dying of smog in London centuries ago. But these problems are now no longer local. And we'll see many examples as we go through this talk this evening of areas in which things that go on in one place affect other things as well. Next. This is the menu of the topics I'd like to bring up tonight. I want to say a little bit at the start about the importance of the kind of science we're talking about to policy and policymakers, and hence to the public. I'm not going to talk much about policy. This is a science talk, but it's certainly true that we would like to see policymakers, when their policies are impacted by the science we do, take account of it. We'd like to see sound science in the service of society. I'm going to tell the story of three of the many, many scientists whose work underlies the subject tonight. I've picked them not quite at random to illustrate several points. And I'm going to start out by reminding you of the history of the ozone hole, because I think it very much is a parable for the topic we're talking about tonight, which is climate change. And then I'll show you some results of changes of the chemical composition of the atmosphere and changes of the temperature of the atmosphere. And then the main point that I'd like to convey to you tonight is a sense of what climate models are. When we talk about the climate models predicting climate change over the 21st century, what indeed is that? What are these tools that scientists use, and how do they work? And then we'll see that the results of these climate models depend sensitively on a few poorly understood aspects of the climate system. And I've selected clouds as an example tonight to talk about. And at the very end, I'll try to make some predictions for the next 40 years as well. Next. On the policy side, I have an up-to-date remark for you from the Bush administration. This is from page 1 of today's New York Times. As you may know, the Bush administration reversed a position it had held during the campaign, which was that carbon dioxide emissions ought to be regulated, and instead said, and I quote, "We must be very careful not to take actions that could harm consumers. This is especially true given the incomplete state of knowledge of the causes of and solutions to global climate change." This was in a letter from the president to Senator Hagel, who is one of the senators who have argued against restricting emissions of carbon dioxide and other so-called greenhouse gases. I think the only comments I'll make on that at this stage are, I agree with the first part as long as we recognize that the actions that could harm consumers include denial and taking no action at all, and that I agree, and all scientists would agree, that the state of our knowledge is incomplete. And I hope that this recognition on the part of the administration is quickly followed up by massive increases in research funding to reduce that problem. Next. Now, the three scientists whose stories I want to tell you a little bit about tonight are Joseph Farman, who led the team of British scientists who were on the ground in Antarctica and who discovered the Antarctic ozone hole. Farman is an interesting character. When I say Farman, he's standing in for the whole team. As usual, the grad students do the work and the professor gets the credit. I mean, the pharaoh didn't really build the pyramids, you know, the grad students did. Farman had been going to Antarctica every year as part of the British Antarctic Survey since the International Geophysical Year in the late 1950s. And this was relatively unsung work. Colleagues often chided Farman for his devotion to this pedestrian business of sitting on the ice and measuring the amount of ozone in the atmosphere. The instrument he was using dated from the 1920s, and that pretty much symbolized the whole field. It was regarded as a kind of dull backwater of observational atmospheric science. All that changed because Farman discovered, quite serendipitously, the ozone hole, the fact that half the ozone in the Antarctic stratosphere disappears every southern hemisphere spring. Charles David Keeling is here at Scripps. He spent his whole career here at Scripps. He came to Scripps at about the same time, late 50s, as Farman started his measurements. In fact, the IGY, the International Geophysical Year, was instrumental in beginning both of the observations. It was Roger Revelle, the founder of UCSD and then director of Scripps, who had a big hand in bringing Keeling to Scripps. And Keeling has devoted his career to measuring the concentration of atmospheric carbon dioxide in the atmosphere. In both cases, I think one would characterize these men as stubborn individualists. They overcame a great deal of hardship and resistance to make the measurements that we now recognize have been of fundamental importance. Lewis Richardson is a different character altogether. He was an eccentric British mathematician, and it was his vision that underlay the climate models that I'll be talking about tonight. And I'll say a little bit more in a moment about each of them, but one characteristic they have in common is that they were ornery individualists. They did what they did because they were driven to do it, because they were curious, not because a committee or a government agency told them to go out and do it. Next. This graphic depicts the nature of the ozone hole. You are looking in a satellite view over Antarctica in two separate years. 1979 is the smaller version up on the upper left. 1989 is the bigger one. The colors depict the amount of ozone in the atmosphere, where the pink and red colors mean lots, the yellow and green ones are little, and the blue ones, and especially dark blue ones, mean very little. It's sometimes asked whether there wasn't always an ozone hole, and the answer is absolutely not. We know that for sure, because we have these measurements stretching back into the 1950s. Ozone started to be depleted only in recent decades, and Farman published the discovery of the ozone hole after going back a few years and checking his measurements and bringing in a new instrument in 1985. So we know the ozone hole is a recent phenomenon, and this story of the ozone hole is a kind of scientific success story, and as I said, also a parable, something that we can learn from. There had been theories in the early 70s by Richardson, by Molina, and Rowland, all of whom received the Nobel Prize for this work in 1995, that predicted the slow decrease in Antarctic ozone amounts, not necessarily Antarctic, in global ozone amounts, due to man-made chemicals, chlorofluorocarbons, that's the freons, and similar chemicals invented by people, didn't exist in nature, invented in the late 1920s, and at that time in widespread use in air conditioning and in industry. And the theoretical prediction, purely by theoretical chemists, was that these chemicals would catalyze the destruction of stratospheric ozone, and the result would be a gradual decrease in ozone amount, maybe 1% per year. It was a concern, and at the time these theories were being discussed in the late 70s, for example, there was a lot of controversy, in a way analogous to the controversy in which tobacco companies have been reluctant to accept the link between smoking and cancer. So the chemical companies, DuPont for example, which made chlorofluorocarbons, made the freons very profitably, poo-pooed the nature initially of the theory, said it was just scientific conjecture, there wasn't any proof of it, no reason to throw people out of jobs and get rid of perfectly helpful and valuable chemicals. The freons, for example, had made refrigeration safe. It used to be unsafe. And it was only the discovery of the ozone hole, the serendipitous discovery by Farman in the mid-80s, that galvanized both the scientific community, the private sector, and governments into doing something about it. And then something was done very remarkably, very quickly. In the matter of a few years, DuPont and the other companies came around. They invented ozone-benign substitutes for the chlorofluorocarbons. The governments passed international treaties, beginning with the Montreal Protocol, subsequently strengthened by other agreements that added more chemicals and accelerated the timetable for their phase-out. And today we can already see a decrease in the stratosphere of the chemicals that are responsible for ozone loss. And the predictions are that if all goes well and nothing unforeseen happens, the Antarctic stratosphere will recover something like its pristine state in something like 40 or 50 years, maybe by 2040 or 2050. So in that sense, it's a success story. We see that science came together because following the discovery of the ozone hole, teams went to Antarctica, satellite data were analyzed. These satellite data, incidentally, are a bit of an embarrassment because you can see that there's data in 1979, and you might ask why the ozone hole wasn't discovered by satellite. It's not quite clear why. It seems maybe the quality control on the satellite data was set to throw out anomalously low values that couldn't possibly exist, or maybe people just weren't looking for it. But in point of fact, the discovery was initially made by Farman and the British team on the ground in Antarctica, subsequently confirmed by satellite measurements, and NASA need not hang its head here because the history of the space agency in monitoring ozone has been glorious since that time. But it's a combination of this observational work from the ground and from space, theoretical work, that unraveled the mystery of the ozone hole. And unlike the story of global warming or the greenhouse effect or climate change, the main subject tonight, there isn't any controversy about this. Everybody accepts what I've just said. It is the man-made chemicals that are responsible for the ozone hole, and it is the benign substitutes for them that are going to be responsible for the healing of it. So it's a triumph of science and politics and industrial innovation. Next. This is Keeling's curve. Scientists, for reasons nobody understands, call every line a curve, no matter what its shape. This is the graph of the rising concentration of carbon dioxide in the atmosphere. There's no controversy about this. Keeling began these measurements in the late 50s. You can see 1958 is the first point. They continue up till today. Nor is there any controversy about why the carbon dioxide concentration in the atmosphere is rising. The units, by the way, are parts per million, which is equivalent to the number of molecules per million molecules. So there were 315 parts per million of carbon dioxide in the atmosphere. It's a very rare gas. You know, it's the same stuff, CO2, that's in beer and champagne and soda. It's a colorless, odorless, non-toxic gas. It's up today close to 370 on annual average. The cause of the increase is you and I burning coal and oil and natural gas. It comes out of our chimneys and our tailpipes. It's an inevitable product of combustion of fossil fuels. We are, as Ravel said, putting the carbon stored in the earth back into the atmosphere in the twinkling of an eye. Geologically speaking, it's a vast, inadvertent geophysical experiment. There are other sources. Deforestation was at one time a major source. It's less of one now. Cement manufacture contributes to CO2. Furthermore, the data are so good that if you detrend them and analyze them in detail, you can see things like El Niños, which affect the amount of carbon dioxide that goes into the ocean. You can see the effects of the Arab oil embargo in the 1970s, for example. People might ask, why does the curve wiggle? Why are there these annual oscillations? And that's an example of the interconnectedness of the Earth system that I was speaking of. The wiggles are the breathing of the biosphere. Every northern hemisphere spring, when the trees put out leaves, carbon dioxide in the atmosphere is converted by photosynthesis into carbon in the trees. And some of that carbon goes back into the atmosphere in the fall when the trees respire. And so you're seeing here an interaction between the trees and the physical climate system. It follows the northern hemisphere seasons because most of the land is in the north, hence most of the trees are in the north. But what you are seeing is clear evidence of the interconnectedness of the physical climate system with the biosphere, the world of living things. Next. Much of what the puzzle in this subject is about is the connection, if any, between that change in the chemical composition of the atmosphere, which is the remarkable result of Keeling's perseverance. Had I much more time, I could tell you wonderful stories. Keeling invented the instrument and that made those measurements. Nobody had one before. There were maps, in fact, of carbon dioxide concentration published, all of which were spurious. They're all sampling error, we know now, because people weren't measuring it accurately enough. Keeling made the instrument much more accurate than he needed to make it. He said he didn't know why, he just felt he should have. It's a remarkable story altogether. And he's still doing it. Unlike Farman, who's retired, and Richardson, who's dead, Keeling is doing that right now. And the original instrument, together with many others, is now chugging away, as it has been for a long time, on the side of the volcano Mauna Loa in Hawaii. This is a record of the surface temperature change. And it's less precise, especially far back. It begins in 1880. The blue lines are the years that were colder than the long-term average. The red lines were warmer. The land and the ocean are averaged together at the top and shown separately in the other lines. And you can see that over this roughly a century and a quarter that these records permit, this is the instrumental record. These are data from thermometers in the atmosphere. The world has warmed up by something like 6 or 7/10 of a degree Celsius, a little over a degree Fahrenheit, perhaps. And you can also see that the warming has been irregular. For example, there was a period between about 1940 and 1970 where there were some red years and some blue years. The warming accelerated in the last 2 decades. The 90s are the warmest year in the instrumental record. 1998 is the warmest year of all. All of the warmest years in recent time are in the 1990s. And if you could see a map of these temperature changes, you would see that the warming has been uneven spatially as well. For example, there's been a lot of warming in far northern continental areas. But nonetheless, it's certainly true that it's warmer now than it was 100 years ago. It's probably true that it's warmer now than it has been for the last 1,000 years on global average, although that's a less certain statement because there are larger errors in trying to infer what the temperature 500 or 1,000 years ago from proxy records. But that there has been warming over the last century and accelerated in the last decades is not in question. I should say right now that warming is just a symptom of climate change. In my celebrated book that Pat Ledden was plugging a moment ago, I liken it to your body temperature as a measure of your health. And talking about climate change only in terms of global average atmospheric temperature or global warming is a trivialization, an oversimplification, as though you and your physician were to agree conspiratorially to only discuss your health in terms of your body temperature. It's certainly true that if your fever is 3 degrees above normal, you're probably sicker than if it's a half a degree above normal, but it doesn't say much about what you've got or what medicine you ought to take for it or what your prospects are. And in the same way, climate change is only characterized by a single number like warming. It might be the best number if you were restricted to 1, but climate change really involves things that affect people, ecosystems. For example, rising sea level is one of the surest consequences of warming, both because the warmer ocean takes up more volume and because some ice on land melts. And in the same way, changes in El Nino, changes in the patterns of hurricanes, changes in precipitation patterns are all aspects of climate change. And so we're using warming here as a simple surrogate for all of that variation of climate. Next. The question is, do these temperatures bear any causal relationship to that carbon dioxide change? The answer is, we're not sure yet, but it seems very likely that in part they do. That's a scientific consensus that many scientists would subscribe to, and the reason we know that is because we've compared the results of measuring the climate of the Earth, temperature being one example, with the predictions of climate models that have been forced or driven by these changes in the greenhouse gas concentrations. We can't put the Earth in a test tube, but we can create a computer program that simulates the Earth and do thought experiments with it. And the reason we can do that owes itself largely to the vision of Louis Richardson, who did his work in the First World War. Again, like Keeling and Farman, he's a colorful character. Richardson was a Quaker. He was educated as a classical mathematical physicist at Cambridge. He was an eccentric, as only the British can produce them. He was fascinated by war, and in the First World War, since as a Quaker he couldn't be a combatant, he found a solution. He drove an ambulance back and forth over the front in France, and in between trips to the front carrying wounded, he carried out the first climate model, or the first numerical weather prediction simulation. He was doing this with hand arithmetic, and I'll say a bit about how he did it. This was the grid he used. You can recognize part of Western Europe there. He picked one of those squares near Munich in southern Germany and said, well, let's predict the changes in the weather in Munich. And if, for example, the wind is blowing from the west, which he could tell if he had observations in each of those squares, and if it were warmer in the west, then you could compute how much warmer it would get in Munich over 6 hours. And he wrote a book published after the war detailing all this. The forecast he made, which took him weeks and weeks of hand calculation, and which he lost after he did it all. It was found after the war. It's a great film. Nobody's ever made it. The forecast was terribly wrong. It was wrong by orders of magnitude. It was physically impossible for the temperature to have changed as fast as he predicted it would. And he recognized that was because the data he had to start with, the observations for today's weather, or what tomorrow's forecast depends on, weren't good enough. But he was incredibly optimistic. He had the courage to publish the method. The book makes great reading even today. And he allowed himself at the end a kind of vision, saying that if you could imagine an amphitheater full of hand calculators, I'm sure he had graduate students in mind, so that they were each working on a part of the problem and handing over their results to their neighbors, so as the temperature in Munich changed, the person computing the temperature in the next grid point would want to know that. Then he thought an amphitheater, or a kind of football stadium that held 64,000 hand calculators, could keep up with the weather. And so in a way he had designed the first massively parallel computer architecture in 1922. Next. Today the climate models we use, and for that matter the weather prediction models on which the prediction that you see every day on television is based, follow directly from Richardson's vision. Here's a cartoon of a modern global model grid. You could imagine dissecting the atmosphere with a regular grid in latitude and longitude and altitude, so it's three-dimensional. And in a modern model, a global grid like that might have points, say 100 kilometers or 100 miles apart, and maybe 10 or 20 or 30 layers in the vertical. So there are tens of thousands of points, and we'll talk in a little bit later about how these models work in detail, but the point to keep in mind, I think, is that not much has changed. Richardson's book in 1922 would be a pretty good starting point for a global climate model developer today. Next. This is the result of running 3 climate models. And this is 3 separate climate models built by 3 groups of scientists in 3 parts of the world. And it's been subjected to the following thought experiment. You know, these thought experiments are the kind of thing Einstein talked about all the time. They're things that you can't actually do, like get in an elevator at the speed of light, but that you can think about doing. In the same way, we can't do this experiment in the physical world, but we can do it in the virtual world of the computer simulation. And the experiment that's being done consists of asking a malevolent, powerful Martian to come to the Earth, instantaneously dump a rocket load of carbon dioxide into the atmosphere, doubling the concentration, then go back to Mars and wait until the climate copes with this insult and comes into equilibrium with the new chemical composition of the atmosphere. So what we do is we run the climate model twice. We ask it once, what is the temperature pattern of today's world? And then we ask it again, what would it be if the carbon dioxide in the atmosphere were doubled? And then we subtract the 2 results. And here's a map of the temperature difference. So the darker the red, the greater the warming. It's just a measure, in other words, of the sensitivity of the climate to carbon dioxide. And the first thing you see is that the models give something in common. There are similarities between these three results. For example, the dark red, the great warming, is all in the far north. Why? Because there are a number of processes that go on in the model, and these three models all include these processes in more or less the same way. And the one that's responsible for this far northern amplification of the warming is that, according to the model, ice and snow melt when the climate warms up. And as they melt, they reveal darker ocean or darker land or trees where the ice and snow were. Those darker substances, surfaces, absorb more sunlight, reflect less than did the ice and snow. And so you have a positive feedback. It's as though you had the thermostat in your house wired funny so that when it got warmer, you turned on the furnace and warmed it up more. And so this positive feedback, known as the ice albedo feedback, albedo is jargon for reflection, comes about because carbon dioxide adds to the greenhouse effect, that is to say, traps some of the heat that would otherwise escape to space. And then that warming melts snow and ice, makes the surface less reflective, absorbs more sunlight, and adds to the warming. And that's in all the models. But you can see that the details, that is to say, the differences from one region to another, are variable from model to model. For example, look at Western Europe, which in the bottom model is largely red, strongly warmed. In the top model is largely yellow, hardly warmed at all. And in the middle model is something in between. This is a classic example of what you will see if you ask climate models what the future climate will be. You will sense agreement, and hence a measure of confidence, some confidence, in the big picture. You will see disagreement in detail. And were I to show you maps of the rainfall or many other aspects of the climate, you would again see similarities and differences. So the state of climate modeling today is that it doesn't agree on the things about climate change that you and I, let alone a congressman running for re-election, would want to know, which is what happens in my district when I'm up for re-election. But you see the big picture. You see a murky picture that is variable in detail and therefore can't fully be trusted, but which is recognizable from model to model in the big picture. We'll talk in a moment about why. Next. Here's the result of a thought experiment. If you ask the model how much the world as a whole warms up, you average all the warming in those maps that we just saw, the answer varies by a factor of 3, and this has been true for quite some time now. This is, again, not a prediction of what the warming will be on a given date in the future. This is a measure of how sensitive the climate is to carbon dioxide. And the answer is something like 1.5 to 4.5 degrees Celsius, say 3 to 8 degrees Fahrenheit in round numbers. That's a big change, and in fact at the high end, at 4.5 degrees, it's comparable to the difference between ice ages and the present interglacial climate, but in the opposite direction. That is a warming on a climate that is already, by geological standards, warmer than average. If you then modify the model, the nice thing about climate models, and the reason they're informative, is that you can go inside and tinker with them and ask how the Earth would behave if it were modeled differently. If you set sea ice constant, so that ice albedo feedback is weakened, and if you then don't let the clouds change in the model, that factor of 3 or 3 degree range between the least and most sensitive models collapses down to 1 degree. So we have evidence from the models that there are parts of the climate system to which the climate is especially sensitive. Next. Now, a climate model is just a computer program. You know, there's no reason to be mystified by it. It's 50,000 lines of Fortran for those of you who are computer people. The climate modelers use outdated language because they haven't learned to move with the world. And it includes not just the atmosphere that I've been talking about so far, but the other components of the climate system that are listed there. And the more ambitious models deal with biological and chemical processes as well as physical things like ice melting. You can think of a climate model as being a kind of summary of what we understand about the climate today. It integrates the knowledge that we think we have, and therefore one of its primary functions is not to make simple forecasts about the future, which are likely to have big uncertainties attached to them, but to teach us, to provide a means of inquiry. Science is a process, you know, it's a way of looking at the world. And you can gain insight from climate models by doing these kind of Gedanken experiments. Next. Now, if you look inside one of these models and ask how they work, here's a short recipe. we set up the grid that we just saw, this three-dimensional grid over the atmosphere, and we start our prediction or our integration or our run with values of the usual weather variables at wind, pressure, temperature, humidity at each of those points. We might get them from measuring, or we might just take average values. And then the form of the equations that underlie these models, the mathematical formalism that characterizes the models, is that the time change for a short period of time for all these variables is a complicated function, depends in a complicated way on the value of the variables themselves. So the equations tell you, they're partial differential equations in time for the mathematicians here. The equations tell you that if you know the distribution of the winds and temperatures and humidities over the grid at a given time, you can compute what they will be for the next few minutes. And then you repeat this as long as you want, till tomorrow or the next day for the daily weather forecast, 100 years out for the climate scenario, and average the results over time and space, just as you would average measurements of the real world to simulate the climate. This is the atmospheric part of the model. You do something comparable for the oceanographic and the other parts of the model. Next. Now, part of the trouble, there's a jargon word that I couldn't figure out a way to avoid, is that much of the things that influence climate are small. If those grid points are 100 miles or so apart, then things like clouds, which are much, much smaller, slip through them. They're not resolved. They go through the model grid the way a bug goes through a coarse window screen. And so the model is full of rules, formulas, algorithms, recipes for relating what goes on the small scale to the variables like humidity and temperature and wind and pressure that are computed on the model grid. So here's an example. If we're computing temperature in Munich, we need to know not only whether the wind blew in warmer or colder air, we need to know whether it's cloudy, because if it's cloudy in the daytime in Munich, less sunlight will reach the surface and warm the air less, and so on. So a possible parameterization, a possible way to solve this problem, is to invent some rule that says, well, I don't know what each little cloud is doing in Munich. They only last 20 minutes and they're too small to see with my model. But if I compute the large-scale relative humidity, maybe I can estimate the clouds. Next, here's an example of a kind of formula you might invent, and this kind of thing is in today's climate models. Here's a graph of relative humidity going from left to right. 0 on the left is dry, and 1 is 100% relative humidity on the right. And you might observationally say, well, I know that if the whole grid volume, that's hundreds of kilometers squared, is saturated, we'll have overcast skies. You can't have a saturated volume of air without clouds everywhere. And on the other hand, if it's dry, if there's no water vapor in the air at all, then we'll have a clear sky. And so the cloud recipe there shows the clouds remaining clear from, that is, at zero cloudiness, up to some threshold relative humidity, which you as a clever theoretician will think up, and then rising as humidity rises until when it's saturated, it's overcast. And you can pick this threshold, and you can pick the shape of this line here, so that your model will give you an overall realistic looking clouds. For example, the real world has about 60% cloud cover on any given day, and you can tune the model by adjusting these features of the little formula in your computer code to reproduce that characteristic. Next. You can then ask the model, or the real world, the answers to interesting questions. Clouds both warm and cool the Earth. You can see the effect of the warming on a cloudy night. If you go camping, you won't be as chilly as you would be on a clear night, because the clouds, like the greenhouse gases like carbon dioxide and water vapor, trap some of the outgoing heat, re-radiate part of it back downwards, and help to keep you warm. And they reflect away sunlight too, so they'll cool you off. You're cooler on an overcast day at the beach than you are on a clear day. You could ask the interesting question, number one here, which dominates today? If you had a planet just like the Earth but with no clouds, would it be cooler or warmer? And that's a question you can only answer by measuring, and the measurements were made in the 80s by satellite, and we know now that the net effect of clouds today is to cool the Earth. The reflection or albedo effect of the cloud dominates over the greenhouse effect. We don't know the answer to the second question. That is, as the climate changes, how will the clouds change, and how will they feed back? Will they amplify the warming, or will they act as a thermostat and damp it down? Next. If you put clouds in your model using that relative humidity formula I showed you, here's the answer you get. You get a positive feedback. That is, the clouds in the model, when you add warming, change so as to amplify the warming. And quickly, because we're getting a little bit complicated now, it happens for two separate kinds of reasons. In the warmer world, the model says there are fewer clouds. That may seem counterintuitive to you, but the model says that in the warmer world, more of the world is like the tropics. There are a few narrow regions where cloudy ascending air exists and many larger regions where clear descending air exists, and that tropical characteristic of the atmosphere occupies a larger fraction of the Earth. So if you doubled carbon dioxide in one of these models, you get a degree or two, a percent or two less cloudiness. Because the clouds in the model, like the clouds in the real world, have a net cooling effect, reducing the cloud amount is an amplifier. It has a warming effect. And the other thing that happens is easier to understand. The clouds in the warmer world are higher. The warm ocean provides energy for these deep convective clouds, thunderstorms in the tropics. They penetrate higher into the atmosphere. And so the average cloud in the warmer world is higher than the present-day clouds. And because it's higher, since temperature decreases with height, it's colder at the top of the mountain than at the bottom, the clouds are on the average colder, and they're also less reflective. Because they're colder, they radiate away heat less well. Physics tells you that how much heat the clouds can radiate to space depends strongly on their temperature. And because they're less reflective, they allow in more sunlight, so they reduce the albedo. So for all of those three reasons, the clouds amplify the warming. Next. Let's summarize a little bit what we've been saying. We've talked about a lot of feedback so far. You can read this graph cumulatively from left to right. Don't take the numbers too literally, but the idea is that the black bar on the far left expresses the fact that if you doubled carbon dioxide, you would raise the world's temperature by about 1 degree. That's a clear physics calculation, and we're confident of that result. Just adding to the greenhouse effect by doubling carbon dioxide is enough to make the atmosphere at the surface a degree warmer. Then all of these positive feedbacks come into play. There's more water vapor in the atmosphere in a warmer world. The evaporation from the ocean is stronger. The hydrologic cycle is accelerated. More water evaporates and precipitates. The ice and snow melt in the far north. And so this 1 degree warming is amplified up to 2 or 3 degrees by those. And then the cloud feedbacks that I just spoke about, the fact that if the model formula for clouds is right, there are fewer clouds and higher clouds, hence more warming, raises the sensitivity of the climate system up to the 4.5 degree level at the top of the range. Whereas different ways of representing clouds, not using that relative humidity formula, but instead keeping track of the amount of water droplets in the cloud and whether it's liquid or ice and so on, can produce a negative feedback. That is to say, in the warmer world there can be more water in the clouds. They can make some clouds more reflective and hence add to the planetary albedo. Right now about 30% of the sunlight that hits the Earth bounces off. It doesn't affect the climate system at all. And most of that 30% is off clouds, 2/3 of it. The other 1/3 is mainly off bright parts of the surface, snow, ice, deserts. But the clouds can get even brighter if some other formula for cloud is used instead of the relative humidity formula. And so in this sense, that range of 1.5 to 4.5 degrees is largely explained by clouds. It's a little bit sobering experience. You can take a great big computer code and change a few lines inside it, which are actually doing all the work, and replicate the sensitivity of the other parameterization if you put it in. In other words, you can use two models. One is a donor, do a transplant of its cloud recipe into the other model, and the new model will respond as did the model from which the cloud recipe came. So much of what's going on in terms of the sensitivity of climate models to carbon dioxide changes is due to a few parts of the climate system which we're not confident about and which are poorly understood. Next. But to which the climate system seems to be especially sensitive. So here's the mantra. Here's one of the take-home messages. We have a lot of cloud parameterizations. You can get one of these climate models free from off the internet, play with it yourself, and invent a new parameterization. In fact, I've done that. I'll show you that in a minute. You can call it your own model. And there are too few observations to test them. I believe, and it's a mainstream view in this field, that the theorists have gotten ahead of the observationalists here, and we have too many plausible theoretical ideas about what clouds could do, and too few measurements against which to test them. Next. Here's an example of that. Here are 3 experiments, numerical experiments done, doubling carbon dioxide. Same idea, the dark red is the greater warming. And you can see here, this is the version of the model that has the relative humidity clouds, and skip over this one for reasons of time. The one at the bottom is one in which the clouds have this brightening effect. And you can see that not only is the sensitivity smaller, that is, there's more green and less red, but that the warming has been pushed far north, so that the mid-continent warming that was apparent in the classical way to treat clouds is largely missing from this alternative way of treating clouds. So you've not only reduced the sensitivity of the model climate to carbon dioxide, but you've altered the geographical fingerprint of the greenhouse warming. Next. The good news about all this comes from the fact that the science community is doing something about this empirical or observational shortfall, and is going to great lengths now to make measurements. And I'm going to mention two kinds of field experiments that are ongoing now that are contributing to reducing this uncertainty in how clouds work. ARM up here stands for the Atmospheric Radiation Measurement Program. It's sponsored by the Department of Energy in this country. Its main field site is an area in Kansas and Oklahoma, which has been staked out for the last 10 years with an incredible array of instruments for measuring everything about the atmosphere. It's the world's best observed climate model grid point by far. It's become a national facility, in effect, because it is so well observed. There are radars, there are weather balloons, there are LIDARs, there are sounders, there are satellites going over, there are drone aircraft with measurements, so that at the same time one can measure all the usual meteorology, the winds and temperatures and humidities and so on, and measure the details of the clouds. Well, where are they, how high are they, how much water is in them, liquid or ice, small particles, large particles, and the radiative properties of the clouds. How much are they contributing to the greenhouse and the albedo? And so we are accumulating a wonderful data set against which to test the measurements. Next. Another field experiment is not being done on a continuing basis, but took place with an intensive period in 1999. This experiment is called Endo X. It was run out of Scripps, a large international experiment with participants from several UCSD departments as well as from Scripps. The co-chief scientists, incidentally, were Ramanathan and Richardson. Richardson, who is at Scripps, was one of the scientists who won the Nobel Prize for the ozone theory. And Ramanathan was actually the scientist who, as a young postdoc, disobeyed his advisor, who told him, don't waste your time on stupid things, and instead looked at the question of whether the freons, the chlorofluorocarbons, could also be greenhouse gases. And he found that they were. It brought him instant fame, proved his advisor wrong. So there's a connection between the ozone story and the climate change story here. What Ramanathan and Richardson and many colleagues from many countries did was to stake out a piece of the Indian Ocean south of India and use the monsoon circulation as a natural laboratory, which successively brought pristine air and polluted air over the region. And what they found was quite shocking. Next, this is a depiction of a result from Endo X, Indian Ocean Experiment, Endo X. And this depicts haze, small particles in the atmosphere. Orange and yellow here are heavily polluted. Blue and dark blue are clean. And you can see here's Saudi Arabia, here's India, here's Southeast Asia, and so on. From India and from China and from other sources, there is an enormous air pollution event going on, largely anthropogenic, largely human-caused, as best we know now, although there's still active research in progress. The sources include fossil fuel burning. There is soot here from diesel exhaust, for example, and biomass burning from cooking fires and heating fires. And this stuff spreads. It's not only heavily polluted here. If you've been in this part of the world recently, you'll know that some of the dirtiest air is in cities in the developing world, where there are few pollution controls, heavy population, increasing reliance on fossil fuels for energy. But it is advected. It is borne away by the winds. And the Endo X scientists could trace this pollution across the Pacific Ocean and find it here in the United States a few days later, borne by the winds. Another example of local effects having global consequences. And these aerosols, or particles, or haze elements, which are caused by people, have powerful effects on the climate in many ways. They can absorb sunlight, they can reflect sunlight, they can nucleate clouds, and we are only just beginning to see their climatic importance. So this is an example of a discovery like Farman's ozone hole that was not predicted by model results, and it has to be incorporated in a fuller understanding. Next. This is a computer model result from a just completed international study, the Intergovernmental Panel on Climate Change, a UN-sponsored agency, and it illustrates the combination of human and natural forcings or effects. What you're looking at here is temperature from 1850 up until the present. The red line is a depiction of the warming that I showed you earlier with the strong warming in recent years. And the left top graph here shows how much of that warming can be accounted for by natural effects. What the modelers have done here is put into their models a representation of how the sun is thought to have varied over that time, based largely on sunspot records, and how volcanoes have varied, because volcanoes also contribute to climate change by putting particles in the air. And you can see that there is some resemblance, but there are also differences. For example, the recent warming can't be accounted for by those effects. The gray area here is the summary of the average, actually, the range of running a climate model several times. And there are results like this from several models, so they're somewhat robust. On the upper right-hand side, you can see the effect only of anthropogenic changes, that is, human-caused changes, in particular adding greenhouse gases to the atmosphere, because we've added carbon dioxide and other gases that contribute to the greenhouse effect. Methane, nitrous oxide, for example, all are increased in recent years due to human causes. And there, again, you see you can reproduce the most recent warming, but there are areas in the middle of the record here, such as this relatively warm period, which don't seem to be accounted for. When they're combined, all forcings means the sunspots, the volcanoes, the greenhouse gases, and a representation of how the aerosols work, then we get a much better correspondence between the model results in the gray and the red line, which is the same on all three panels, the observed temperature change. That's the tip of the iceberg of the evidence for thinking that the correspondence between model predictions of climate change and observations of real climate change is good enough that it seems unlikely that all the observed climate change can be due to natural causes. The delicate, negotiated, weasel word, lawyerly language that's actually used in the recent report is the balance of evidence suggests a discernible human influence on climate change. There's a lot of caveats there. But it seems unlikely that all the climate change could be due to natural causes. And in fact, if you ask scientists what the climate change will be in the future, the arguments tend to be quantitative. Where and when and how strong will the climate changes be that we see? Okay, next please. There are a few messages I'd like to leave you with at the end. I said, and I'd like you to take this message home, if you will, that it is a trivialization of an important and complex scientific and geopolitical issue to think of climate variability as simply being global warming. It has a nice journalistic catchy ring to it, but keep in mind, please, that climate change involves aspects of the climate system, sea level rise, changes in storm patterns, changes in El Niños, hurricanes, that will affect human life and other life on Earth in powerful ways. And global warming doesn't do justice to the range of climatic effects. In fact, you will hear people say, I moved from Denver to San Diego and the temperature went up by more than 3 degrees and it didn't hurt me that much. I'm pretty happy. And that's an example of choosing an inappropriate metaphor, I think, in which to express a scientific result to a larger audience. Next. I think that there's been remarkable research progress and great promise of future progress in these areas of testing the aspects of the climate models to which the results are so sensitive against observations of the real climate system. Again, it's a classical example of the interplay between theory and measurement in science. It was typified in the ozone hole. Again, a reason for calling that a paradigm or a parable for this kind of science. But it's really true now that we are, and we see in the future to an even greater degree, able to observe the atmosphere in ways that will let us test our theoretical notions against measurements of the real world and therefore decrease the uncertainties that characterize climate models. Next. Finally, I haven't talked much about this, but the nature of climate modeling has changed. It used to be 40 years or so ago, this is a 40-40 lecture, we're looking back 40 years, when Keeling began his measurements, when Farman began his measurements of ozone. At that time, when climate modeling was in its infancy, climate codes, these computer programs, were proprietary. They were closely held. They belonged to a small number of laboratories that could afford a staff and a supercomputer in the basement. Today, there are scores of these models available. You can download them for free from the internet. You can run them on a workstation. You can probably run them on a PC. And therefore, there's a less intellectual conservatism to this field. There's more willingness to experiment. Graduate students take these models and find bugs in the codes and invent newer and better versions. There are email chat rooms in which people exchange reports of their experiments. There's a plug compatibility taken over from the weather prediction world, so that if I invent a different recipe for clouds, somebody in France or Japan can put my recipe into their models, because the overall structure of the models has these common hooking up points for changing bits of physics. I think because it's cheap now, Moore's law means that it keeps getting cheaper to compute faster. There's more creativity. It used to take months of time on the wall clock to do one of these climate runs. Now it takes a few minutes on the workstation, and so people are willing to try wild and crazy off-the-wall ideas, and that's essential to progress. And on good days, I even think there's more collegiality. There's more willingness to be less competitive about this. Next. I want to leave you with the message that I started out with, that this kind of progress is driven by a combination of big science. We've talked about satellites and computing power, but also the insights of a few individuals who persevered in pursuing what was, to the eyes of many other people, an unprofitable and unpromising line of research. And the future Farmans and Keelings and Richardsons are among us. There are some Scripps graduate students here in the audience tonight, for example. I hope, as I said, that President Bush will back up his conviction that the science is incomplete with directions to his agencies to support more of it. And next, I think the summary, next to the very last thing I want to say is that keep in mind that the climate is sensitive, as best as we can tell from models and observations, to a few bits of physics. I've mentioned clouds, I've mentioned particles in the atmosphere. There are other topics, too, that had we more time I could have mentioned. The exchange between the ocean and the atmosphere of heat and momentum and water, for example. There are aspects of the biological and geochemical aspects of the climate system that certainly are just at the fringe of being understood well enough to incorporate in models. But keep in mind, there's not an infinity of these things. There's reason to think that we can make progress on the important ones. The parameterizations, the rules for incorporating small-scale processes, have until recently been very conjectural and have lacked a true observational basis. That's changing now. And I'm an optimist. I think many people in this field are happy to be working in it at this time, because this combination of new observational data and improvements in the theory and computational side of things, it augurs very well for the future of the subject. You've been very patient, and I thank you very much. Well, the question was, there's a potential for large amounts of additional greenhouse gases to be released from methane hydrates that are currently trapped, but it hasn't been mentioned here. I think the short answer to that question is that the models in the context about which I've been speaking tonight are driven by an arbitrary prescribed scenario. Someone decides, let's see what would happen if greenhouse gases grow at a given rate. And predicting what greenhouse gases will be in the future is very difficult. It depends not only on the physical climate system, how much methane is going to be released in the future, but on decisions that people will take. So it depends on how many people there are on the Earth. This is very population-driven. People don't realize that the population of this planet has tripled in the last 70 years. It was 2 billion in 1930, and it's 6 billion plus today. And in fact, the anthropogenic sources, the people-caused sources, are shifting rapidly. The US today is the largest single emitter of carbon dioxide, emitting somewhere between 20 and 25%. That's likely to change, and the US is likely to be overtaken by China in this dubious battle because there are simply so many more Chinese, and China is largely industrializing on coal. As the developing world consumes more and more resources, if it energizes on fossil fuels, as the West has done, then the pattern of emissions will change. If the world goes nuclear, the way France has, for example, the pattern may change in the other way. If greenhouse gases are released from natural sources, as the questioner suggested, that can be a different source. We don't yet have a clear understanding of what it will take to cause rapid release of methane. Most of the methane increase today appears to be leakage from natural gas lines and combustion also. Methane is basically natural gas. So I think I've given you a roundabout answer, but the short summary is to say that in the sorts of modeling exercises that we're doing today, the greenhouse gases are an assumed input into the model. So you can assume a massive increase of methane if you like, and then compute what the climate response has been. But the bulk of the effort today has gone into simulating the effects of gradual increases in the concentrations due mainly to human sources.
So it's being ignored?
I wouldn't say ignored so much as not emphasized. It's not a difficult calculation to do. What's difficult is to predict how much methane will be released. The fact that there has been geological precedent doesn't tell you what's going to happen in 2020 or 2050, but you could do that. In fact, I will agree with you to the extent that I think the scenarios that have been run have been conservative. One talks about doubling carbon dioxide, and it's very likely we will have done the equivalent of doubling pre-industrial carbon dioxide very soon when you add to the carbon dioxide all the other gases, which in sum might be equivalent to the carbon dioxide. You might as well ask, what about tripling or quadrupling or quintupling carbon dioxide? And there's been very little work on, you might say, massive changes in the chemical composition of the atmosphere. To that extent, I think you make a very good point. The question was about the climatic effects of the fires in the oil fields following the Gulf War. Some forecasts had been that there would be widespread climatic effects, and in fact, there were strong local effects, and of course, locally it was an ecological disaster in many ways, but there don't seem to have been widespread effects. In fact, it was hard to talk about the Gulf War as being a fortuitous experience, but just because those fires were set, the science community did mobilize, and a lot of observations were made in the aftermath of the war around those fires and downwind of them. And apparently the smoke and soot settled out, so that far from the fires you didn't see a big environmental effect. I titled this talk, Can Climate Models Be Trusted? And I think the answers to those questions are, in part, yes, they can. In part, there are questions we'd like this science to answer that it hasn't been able to yet, just as we could say that about medical science. But because the climate predictions on the scales that we can test them, predictions of El Niños, for example, or seasonal climate change, are better than chance, and because we are using the same models to make skillful short-range weather forecasts, and because we can simulate the effects of Pinatubo, and in many other ways validate aspects of the models, the answer is, I think, that they can be partially trusted, and one should treat them that way as great machines that can give you answers that you should take seriously, but not always literally.
I think we should thank our speaker for a very remarkable